at on whether we could find evidence that there was a partially genetic basis or a heritability for human network topology. And we found, for instance, that people varied in their tendency to have friendships, and that this variation was quantifiable, and they also varied in certain other ways we can discuss if you're interested. But eventually we showed that in a paper we published in PNAS a couple of years ago now, we showed that the topology of a person's network is partially heritable. Where you are in a network depends in part on your genes. Are you in the center or in the periphery? Do your friends know each other? How many friends do you have? And so forth. And then in a subsequent paper, also in PNAS, we found that there was an association between the genes, the genotypes of some individuals and the genotypes of the people around them. So people occupied sort of genetic niches in networks, and in fact, you are swimming in the genes of your friends. So your outcomes may depend not only on your own genotype, but also on the genotype of the people around you, and you pick those people as your social contacts. So that begins to provide a hint as to the basis by which evolution might act on human networks, creating these long feedback loops across evolutionary time. Mapped the social networks of the Hadza hunter-gatherers. So there are only about 1,000 of these people left. Only about 700 of them live in the traditional way, about 400 or 500 adults. And Corinne went to Tanzania. These people live, they have no material possessions, they sleep under the stars, they hunt and they gather for their food. They live like we humans did tens of thousands of years ago. So Corinne spent the summer driving around Hadza land, and we made these big posters. We had a photographic census of all the adult Hadza, and we made like a Hadza Facebook. And we took these posters to the field, and every Hadza adult, we asked them to identify their friends in various ways, and we mapped the networks. And the astonishing thing is, by every measure we could throw at it, Hadza social networks look just like ours, mathematically. The same degree distribution, the same amount of transitivity, same extent of homophily and reciprocity, same decay with geographic distance. And then while we were there, we also measured the individual's propensity to cooperate, and we found, as hypothesized, a very deep relationship between human cooperation and network structure. Some physicists and others have modeled, for instance, what type of network structure would be optimal to retard the flow of a pathogen through a network. And this will probably make intuitive sense to you, but it turns out that degree assortativity is very good, is very helpful when you're trying to slow the spread of a pathogen within a network. Well, we know that human populations evince degree assortativity. So maybe we evolved to have networks with particular properties because they make us as a group more resistant to the flow of germs within the system. So there may be a variety of structural features of human networks which are adaptive. We don't yet fully know what those selection pressures were, like why we might have the certain features that we do. But many of the features that networks evince, that human networks evince, you can make a good argument for why that is functional, why that's beneficial. You know, I recognize that group selection is sort of a minority view. I'm not saying that there's no individual level selection. There clearly is. But I think that some of our work does provide more of a basis for understanding group selection, you know, even outside the eusocial insects, for example, and the arguments that are being made there. So I think that, because if you begin to understand that my fitness depends, by fitness I mean Darwinian fitness, that my fitness depends not only on my own genes, but on the genes of my neighbors, and moreover that I select my neighbors, and that we form assemblages with particular mathematical properties, then you can begin to see that my phenotype and my fitness might depend on the genotype not just of myself but of those around me, which provides a lever or a mechanism to have group selection. One of my favorite examples of this is work done by other scientists that's looked at caged hens. And they looked at the feather condition of these hens, and the hens The feather condition of a hen is a very important phenotype in a hen. And they found that the feather condition of the hen depended not only on the genotype of the hen, so some hens had better feathers than other hens did, and it was related to the genes that they had, but also that the phenotype, the feather condition, depended on the genotypes of the other hens that were caged near it. Yeah. So those other hens might be aggressive hens that are pecking on you, right? And that causes your feathers to be worse. So, and in fact, they found that your feather condition depended more on the genotypes of the other hens around you even than on your genotype. Well, what's interesting about that experiment, and then you could, of course, randomly manipulate that, what's interesting about those studies is that in humans, we pick the people around us, right? So
except in jail.
In jail, well, you could look in jail. That's right, exactly. That's exactly right, except in jail. But you could begin to imagine now a kind of broad feedback loop whereby we humans construct a social environment around us. That social environment is a kind of selection pressure. Look, the leading threat to other humans, the leading predator of other humans, has always been other humans. I mean, the main thing that kills us is not lions, but other members of our own species. So we can adapt to that pressure. The existence of other humans, they're a source of support, but they're also a threat to us. So this is actually one of the reasons we think that cooperation is also part of the story. The necessity of cooperating with others, of manipulating network structure to foster cooperation and to preserve cooperation. Identify central people in networks and monitor them, either actively or passively. You can forecast the future of an epidemic. Because the intuition is that central people are going to be more likely to get whatever's spreading in the network and more likely to get it sooner, so they should have symptoms of a disease well before the average person. So if you can identify central people and monitor them for symptoms, you can forecast that an epidemic is coming weeks ahead of time. And in fact, we demonstrated that this was possible with the outbreak of H1N1 flu a couple of years ago, and we also published that paper. But since then, we've begun to think about other things that you can do where you could, for instance, in the developing world, how could you exploit an understanding of network structure and interaction to enhance the ability of villages or groups of people to improve their health and their well-being. So for instance, could you target particular interventions like new technologies, malaria bed nets or vaccination or drugs of particular kinds or new seed technology for the farmers to use. And if you can map the networks of these villages, can you figure out who are the best people to target so that if they change their behavior, the whole group will change? Can you get a phase transition in the network by exploiting what you know of how they work? And so this is another set of things that we've been starting to do.
Time never really on my side. When I look what I find is only shadows in my mind. Time, do I really have to stand still?